When you look at biological systems, muscle fibers glide silently, but our modern robots still rely on grinding, rigid, cylindrical servomotors. To get the fluid-driven motion that mimics human flexibility, engineers typically have to tether their machines to a heavy umbilical cord of bulky air compressors and noisy external reservoirs. That massive external plumbing creates a severe design limit. You cannot strap 100 pounds of clanking metal compressors to a person's body and call it an everyday mobility aid. Now, researchers from MIT and Politecnico de Bari have solved this with electrofluidic fiber muscles, completely soft threads under 2 millimeters thick. Instead of bolting a heavy motor onto a frame, they figured out how to stretch the entire power and actuation system into a flexible strand of yarn. To actually sever the connection to those bulky external tanks, the research team completely rethought fluid dynamics by building the pump right inside the fiber. When fluid enters, this McKibben actuator expands radially and contracts in length. To move fluid silently, an internal electrohydrodynamic pump uses electric fields to drag ions forward. Pairing a second fiber creates a closed loop. As one contracts, it pushes fluid into the other. Because the relaxing side acts as the holding tank for the contracting side, the system's mass remains constant. You get fluid power entirely self-contained within the thread itself. This chart shows the internal system pressure during operation. To make this closed loop work, the engineers have to apply what's called bias pressure, elevating the entire baseline well above atmospheric levels. Pre-pressurizing the system ensures the relaxing fiber doesn't simply collapse under the strain. More importantly, it stops vapor bubbles, or cavitation, from forming and destroying the delicate internal pump. Once that individual thread is stable, scaling the technology becomes remarkably straightforward. If you need an engine to pull harder, you don't build a larger, heavier machine, you just tie more threads together. A tightly braided bundle of these fibers successfully hoisted a 4-kilogram load, moving 200 times its own weight in total silence. You can also rewire that architecture for speed. By wiring multiple internal pumps to a single actuator, the fibers can contract fast enough to launch an object in under 300 milliseconds. This modularity clears the bottleneck of robotic scaling. By matching the 50 watts per kilogram power density of human skeletal muscle, engineers have a universal building block that can be tailored for any physical task. But stacking threads to lift heavy industrial blocks is only a fraction of what this architecture can do. The real advantage lies in how these fibers interact with the human body. Because the power and actuation are completely distributed, these fibers can be woven directly into sheets of fabric, creating an active textile that wraps and bends like biological skin. Crucially, this soft material possesses a property called backdrivability. If an external force pushes against the woven muscle, the fluid naturally gives way instead of fighting back. Unlike rigid servos that can easily crush fingers, this inherent compliance means humans and machines can safely interact with a gentle handshake. We are looking at the foundation for assistive clothing that helps the elderly walk upstairs without carrying extra weight, or prosthetic limbs that finally mimic the quiet grace of a natural arm. For decades, the vision of human augmentation meant bolting ourselves into heavy, rigid mechanical suits. Tomorrow's assistive technology won't be a clunky exoskeleton at all. It will be a silent, powerful garment that moves right along with you.